Okay, so we're back with our friendly mass on a spring. You say, why do we spend so much time on the mass on the spring? Well, it's because it applies to so much physics, right? It is the way we model solids. I mean, it's the basic model of how a bridge works, right? When a car drives over, I mean, not only model solids from a chemistry point of view or a quantum mechanical point of view, but how a bridge works. When we drive a car over a bridge, the bridge has to react to the car driving on the bridge. It squishes, and it squishes like the car is a mass and the bridge is a spring. And we need to start with this model for any engineering project, right? We need to understand this model, how bodies react to forces. They react like masses on a spring. It might be more complicated, it might be damped, it might be driven, etc. But and it might be more complicated than a spring constant of k. But we have to understand this model in order to understand a large array of problems in physics and engineering. Again, let me just say, buildings, floors, bridges, things that hold things up, they are all springs that react to masses. Okay, so let's just ask now let's just focus on the mass on the spring and say we know it's going to oscillate around equilibrium, some distance x from equilibrium, and x is as a function of t is as given. What is the speed or the velocity of this mass as it moves, right? Think about it. If we pull the mass out to some maximum distance from equilibrium and we let it go and we let it oscillate up and down, where is its velocity of maximum? Where is its minimum? We pull it out from equilibrium and we let it go from rest at the maximum, right? X max equals A. At that point, then V equals 0, right? V0 equals 0. And it speeds up as it gets close to equilibrium. But if we get past equilibrium, now the spring is pushing back and it slows down until it gets up here. Whoops, it's not V0, where V equals 0 again. So where's its fastest speed? Its fastest speed is in the middle, V max, right? That's its fastest speed. You could also think about acceleration. What about the acceleration of the mass? The acceleration is not constant. This is not constant acceleration problem, right? If this is the equilibrium position, the center position of the equilibrium position, that is by definition where F equilibrium, the force at the net force at the equilibrium position is 0. That means the acceleration is 0. So I'm not sure that should say F equilibrium equals 0. It's not wrong, but the acceleration is 0 at the equilibrium position. Even if it's moving through the equilibrium position, that is where the acceleration is 0. That's where the net force is equal to 0. And the acceleration is a maximum at the endpoints when it comes to a stop and it's turning around. It's not the acceleration is constant, like when you throw a ball straight up at the top, the acceleration is still constant. That's actually where the acceleration is a maximum. Let's show that. It might not be obvious. So how do we show that? Well, remember that the velocity of the mass in the spring is just dx dt. So we can take the derivative, and what we get is when we take the derivative of this function, we get a omega cosine omega t plus phi. Hopefully you can take the derivative of that. And this is the velocity function. There you go. That's the velocity function. What's V max? Well, what's V max? V max, the maximum velocity, is a omega because the maximum of the cosine function is 1. It's a omega, or a square root of k over m, right? A is how far we pulled it out. So the farther we pull it out, the bigger the V max. Which again occurs at the center point. Oh, how do I know it occurs at the center point? Well, this is a cosine function. Where is... I just realized it's probably easier to answer the question, where is V max, to first of all plot x versus t. We should plot x versus t. So the position x versus t, if let's start t equals 0 when we're a maximum away. Nope, sorry. Oh, sorry. Let's just say that we have the mass oscillating on the spring, and we can start t equals 0 wherever we want, but just for the simplicity of the math, I'm going to say let's start t equals 0 when x equals 0. So if x equals 0 when t equals 0, therefore, again, remember what that defines for us is phi, and that's what I'm trying to do here, is therefore 0 equals a sine square root of k over m times 0 plus phi, and then we solve for phi. So 0 equals sine phi, and when does sine phi equal 0? Well, that occurs at phi equals 0 degrees. It also occurs at phi equals pi, at phi equals 2 pi, etc., right? And we can use any of those because it's repeating motion. So it is true that the sine of phi is 0 at many different places. But the first time it's 0, let's just say, it's when phi equals 0. So we'll set phi equal. I mean, we can set phi equal to. I guess here's my point: is we can set phi equal to any one of these things. Let's make it 0 to make it easy. So we're going to graph x equals sine omega t. Phi is 0. So how do we graph x equals a sine omega t? Well, that looks like this function here. That looks like that function where this is a. Oops, this is a. This is also a, right? The magnitude of that distance is a. The amplitude. I don't know what else we can show on this. Oh yeah, we could actually show that. Right, this distance here, this is the period, t, which is, what is that, 2 pi square root of m over k, whatever that was. Doesn't matter, we had figured that out before. Well, actually it does matter. T is equal to, okay, let's just make sure. Omega is equal to 2 pi f, so f is omega over 2 pi, and period is 1 over that. Yeah, so that gives us what I wrote there. So this is a graph of x versus t. And the phase factor, notice the phase factor really just tells you where we start. Tells us where we start. If I had said we start the stopwatch where x is a max when t equals 0, then instead the x-axis would be through this point here. And that would basically what we would say is that shifts the curve back by a phase. It shifts it by a phase, by quarter of a wavelength. It shifts it back by a quarter of a wavelength. Is that a quarter of a wavelength? Yeah, that's a quarter of a wavelength. I think that's a quarter of a wavelength. Yeah, it is. Okay. So that's the phase factor. Okay. Anyway, don't worry about that. We're starting at x equals 0, t equals 0. So now let's look at the velocity function. Velocity as a function of time. Notice that the velocity is a cosine function. And so where x is going to be minimum, v is going to be maximum. That's just because cosine versus sine, that's true. And so we're going to get something like this. I don't know if I'm drawing it to the same scale. I mean to be. So where, I'm trying to show where it's a maximum. I didn't do a very good job. Where it's a maximum, where x is a maximum, v is a minimum. Where x is a minimum, v is a maximum. Okay. So what this shows you is that if I take this equation here and I set the phase equal to 0 because it is, given this problem, v is equal to a omega cosine omega t, and we ask, so the original question is when or where is v a maximum? Not when in time, but where is v a maximum? And I said I claimed v was a maximum at the center, right? What you can see is that since x equals a sine omega t and v equals a omega cosine omega t, you can see that when x is a maximum, v must be a minimum, and when x is a minimum, v must be a maximum. Phew, that's what I was trying to show, is that because they're just the opposite function, one's a sine and one's a cosine, doesn't matter that one's a and the other's a omega, you can still see that when sine is a minimum, cosine is a maximum. When sine is a maximum, cosine is a minimum. So that means when x is a minimum at equilibrium, velocity is a maximum. When x is a maximum at the endpoints, velocity is a minimum. Okay. Let's go ahead and take a second derivative and write down the acceleration. So therefore, acceleration is dv dt, which is a omega squared sine omega t plus phi in general. I know for this specific one, phi was 0. But anyway, and there's a minus sign that comes out. So what is a max? The maximum acceleration is a omega squared, right? Or the absolute value of minus a omega squared. If the maximum acceleration, we're not talking about direction. Minus just is direction. Whoops, I threw my pencil across the room because I was so enthusiastic. I'll be right back. The minus sign indicates direction, so the magnitude of the maximum acceleration is a omega squared. And notice that it's got the same function as the position. So where x is maximum, a is maximum. Where x is minimum, a is minimum. So the acceleration is 0 at equilibrium where x is 0. The acceleration is maximum where x is equal to capital A, the amplitude. Oh, careful. Here I'm talking about a acceleration is equal to amplitude times omega squared, but doesn't matter. A acceleration, the acceleration, in my picture here, is 0 where x is 0, and the acceleration is a maximum when x is a maximum. The acceleration is not shown in this, at the endpoints is not shown here, but I'm saying that acceleration is a maximum where x is a maximum because it's the same function. So that's everything. Now I have really beat this derivation to death. We've shown the equation of motion for x as a function of t, v as a function of t, a as a function of t, acceleration. We defined all our variables. And we'll do a quick example or two before we move on to pendula. Happy day.